Good day. Welcome to PLC3 Analog or Week 6 Analog I/O. You're watching this because you clicked the link here for the video, so we will get into it. I gave you some new handouts last week on the homework, the lab, and not in the handouts, but there's lots of reading on D2L about analog basics. So just to reiterate, we skipped the full analog lecture for some of you last time in ELTE 261. And so we're going to just kind of run the whole thing here and get you into some analog basics and a few other things that are going to be really interesting. Before we get that, let's do our week 5 review. And you know, I had a lot of stuff here for the barcode scanner. Hang on one second, my computer just glitched a little bit. All right, that's fine. I had a lot of stuff for the barcodes. We only got through the handhelds, which is fine. We'll use more of the industrial one that can be event or time driven, that scanner for the capstone, and bring some stuff in there. But what we did is we set up the handheld Cognex scanners, new in the box. You know, you might do that someday. We had to download the vendor software, the data man. It was interesting that we had, you know, some issues with that, you know, because technology moves fast. We'll talk about it a little bit. We downloaded the add-on profile and the EDS files so that the software, the RS links and the RS logics could seamlessly see the barcode scanners and have controller tags, and links would see it all and all that kind of stuff. So the issues that we were having was that, you know, like technology moves fast, so we're having hardware and software compatibility with Windows 11 or Windows 10e, you know, the latest version or the oldest version. And we did a good job of working our way through that. It took us an extra hour to get it to work, unfortunately. But that's par for the course. And the students did a good job of kind of using the internet and to search databases and forms and stuff like that to try and figure out why it wouldn't scan. Did we need older software? And what we had to do is we did have to use one of the barcodes that are available to enable the Ethernet, for example, in order for links to get it to read. In order to set the IP, we had to use an older version on Windows 10e, you know, things like this. But like I said, the barcodes are available to do setup, factory reset, you know, just all your communication stuff like that. We had to use a couple of them. And then it was power over Ethernet. We did a good job of not blowing anything up. And, you know, just hooking those up and getting them to read. And it was pretty painless getting those to read. And the barcode scanners, and we just kind of set it up with the Cognex software, the data man, and we created and scanned different styles of barcodes, 1 and 2D barcodes, just so that we could see how it populates and how we could potentially save it into a file. If we were taking a lot of data from a barcode reader, we might not use a PLC. We might use some type of a database software to collect that data into a file, and that's what we did. We then got it hooked up to the PLC, and we saw that the data comes in a little, I call it messy, and we'll talk about it. And we needed to manipulate that data a little bit, okay? So PLC can store this data, but, you know, if you're really doing a lot of data, you might have some other type of database software that would maybe work a little more seamlessly with this. But if you were using the PLC to have that barcode call up a recipe, or, you know, store some basics stuff or trigger different subroutines, stuff like that, certainly, you know, that I'm sure that you could see how that is, and we'll talk about part tracking in a minute. So just to reiterate, we did data types in PLC1, ints and dints and reels and all this kind of stuff. We haven't really worked with reels yet. That's what we'll be doing this time in Booleans. And we talked about ASCII, but we didn't do much with it. So ASCII, by the way, it's in letter, number, symbols, 128 unit code. Brings in, you know, different items from the English language as well as control characters. And for example, I just look at G right here. It's 01000111 is G, right? And so it brings in, like I said, letters and some control characters here. And that's what that, when I say messy, that's kind of what it was bringing in. You set it up so the barcode would bring in, an SINT, such as 11001100, because that's kind of the smallest data type, 128, for something other than a bool, and that's what is that this ASCII is set up for here, is 0 to 127, 128, different combinations, right? And then you have, because 8-bit bytes, and that allows the PLC to interpret the byte array as an ASCII string. So when we got that ASCII string, and like I said, it was messy. So we used STOD string to convert that ASCII string to a 32-bit signed integer. Okay, and then the PLC seemed to do a little bit better with it. There certainly was some issues with that as well, because who wants to look at a G as 01000111? You want that as a G, and so we did mess around, bringing in numbers straight off of a barcode, like you might see on a soda can or something like that. But then we also wanted to bring in like your name and bring that data type in as a string, and then we put those into user-defined tabs. So we had tags. So we had a combination of your name and the date stamp and the part number and stuff like that, right? But backing up to the STOD, when it was coming in, it was ignoring any non-numerical characters. It started the string, it sets leading minus to handle negatives. It reads the first sequence of numbers. The process terminates when it finds a non-digit character. So that was good, except that we were reading in more than one. Let's say we set this up in the Dataman software would let me read my name and a number, and we typed the color red and stuff like that, and it would build a little array. But if you did that on the PLC, you could do that. The problem is it's coming in here as a string here, and we already said this, Sean, is going to be messy because this S is going to be 01010011. This is fine, and kind of this is going to be compacted into ones and zeros, binary, and then red and 3 anyway. So this would be coming pretty ugly. Notice that when this comes in, there's a delimiter. Here I put a comma, but depending on what process you're using to bring stuff in, there's probably going to be some delimiter between the different items that you want to read. So you can mess around with this if you get this messy file, and just some of the things, some of the commands that instructions that are similar to this, whatever PLC you're on, whatever, or whatever database, or however you're looking at this, computers. There's things such as find search. It locates the starting position of a specific substring in a larger string. So you might be able to put in, the delimiter or how many delimiters or special character, whatever, and then it would find that location, and then it might capture all the data here and then stop when it finds the next delimiter, and it would parse that string. You could parse this string into 1, 2, 3, 4 different separate pieces of data instead of just one data, right? Concat, you can combine strings. LEN is a good one. We did use the .len off of the control. When we put that in, it came with a control from the from the scanner setup, we got a controller tag, a control, and one of the things was the LEN in there so that we could determine the length of the string, which is great because that means that you can scan multiple things. They don't necessarily all need to be the same length, and it will process the data as you go. ASCII to string to real, integer, string to real. We were kind of doing that. Mid extracts a specific number of characters. Once again, if you wanted to parse this, you could use the mid, and then you could use the mid in conjunction with the length to determine what the delimiter was, and parse this out Find there's locations to start in the substring. You can delete parts of the substring. So if this came in, you could cut it all up, and we didn't have one student who was having a great time cutting all this up, but we're not going to do it too much. What we did, instead of just reading all of this in right here, we just took a couple of scans. We took a scan of the operator and a scan of, I guess, the part number or the item or something like that, and then we generated our UDT based on multiple scans with a barcode scanner. Whereas really you could just hit this all, you can put all this into a barcode and then just scan one thing. But we just kind of getting the gist of it. Like I said, the add-on profile, and that improved the integration with Studio 5000. It created your controller tags. That's what I was talking about. You get your control, so you can use your .len tag, controller tag. And it's just great for your device recognition. We didn't have to scan the barcode to get that to look up in links. Our electronic data sheet, that's what we had. It facilitates communication with the RS links, and RS links is embedded in Studio 5000. So we were having some interesting issues with this. Like, initially when it came in, we were getting the device showing, but it had like a yellow question mark. The thing still works that way. If you have the add-on profile on, you'll still have your controller tags. But if you get that, it won't be totally happy, but it will work. What was interesting then, when we finally did load up the EDSs, it just went away. We couldn't even find it at all. And so once we scanned that barcode to enable Ethernet I/O, then bang, it popped right back up. So once again, great little learning activities about the ups and downs of Allen Bradley software, hardware, programming, initializing equipment, everything like that. We did talk about part tracking. We didn't use BitShift. We did a lot of that before. We were just messing with some FIFOs, collecting user-defined tags. We went over user-defined tags. I think everybody sees the value of a user-defined tag. I'll talk about get a system variable later with that. But the user-defined tag is where we kind of boxed up a string or a bool and or a dent. We could put it all in to a user-defined tag. And then we could even stack that user-defined tag up in a FIFO as we collected data and then load it and unload it. As far as getting the system variables, that was, you use your GSV. We probably, a good way to do it would have been to create a user-defined tag with 6 members. And the members being year, month, day, hour, minute, seconds. There's actual microseconds too if you wanted to do that. And then you have your all that data there. And so you take the picture and it records all this every time you scanned or something like that. You wanted the timestamp for it. Now, getting to the HMI is a little bit of an issue because you have a UDT with 6 different fields. So I guess you could make put 6 different fields all in a row on the HMI and just have each one of those fields look in. The first one looking for the year, the second one looking for the month or the day or the hour or whatever order you want it, and put it up on the HMI. And the same thing if you threw all of this into your UDT, which you could have a UDT within a UDT. It might be kind of hard to figure out, to track down what year and month it was if you were stacking up the variables and everything like that. So I guess what I mean, it'll work. I'm fine with it. But what you could do is, I guess you could convert, all those items to a string and then combine them and then store them like that. And then that way, when you have the HMI, you just push out one thing. And then when you store the data, you just save one thing instead of, 6 different members. It might be a little cleaner that way. But I think, I don't know, we had a couple students messing around with it, just a little bit of a pain in the butt. The barcode scanners do have timestamp. And I'm thinking that the more advanced ones will come with a timestamp that will be a controller tag that you can grab. But you can set them up. It just requires a little bit more a lot more of kind of an advanced setup to get that barcode scanner to push that out. So if you get some barcode scanners, you're just just like we learned here, man. You gotta dig into it and figure out how they work, what they're capable of. There's just hundreds and hundreds of pages of multiple manuals to get this to work. But hey, they'll do what you want. And as you know, we ran a problem and I called tech support. You can always call tech support, although tech support didn't know what the heck was happening. We figured it out on our own, and that's pretty common too. So anything else? Yeah, once again, the labs are pretty involved. I'm okay with people kind of learning at their own pace. Everybody's picking up something. You're getting around pretty good. You're understanding how all this hardware and software and logics works and everything like that. So hopefully everybody's kind of now staying caught up so that we can move on to the analog part of this. All right. So for the homework review, you read the basics about barcode scanners, and then we have a quiz on that after this, just kind of that barcode lab. And then you read the basics and submitted that for the analog lecture, that we're going to do now. All right. So for the analog, we talk about resolution. That's the smallest change in input signal value that can be measured. Sometimes you want high resolution, sometimes you don't really need it. And that really is just relative about, what is high resolution and what is low resolution. It totally depends on your application about, how much resolution that you want. And I could go into it, if you're doing something super scientific, super high end, you might need incredible resolution. Whereas if you're in manufacturing, maybe kind of some gross resolution might work better. So when we hook up our input and output analogs, and we'll be doing this for the next couple of weeks, it's pretty similar. There's sourcing or syncing. It can be in the current loop can be supplied by the sensor or the module. As we get into it, and we're hooking up, I'm going to be giving you a lot of wiring diagrams and a lot of new trainers that I just put together recently. I just want you to follow the instructions, check with the wiring before you blow anything up. This analog stuff's could be a little more touchy than the diagnostic digital input and output modules we've been using. So let's just be careful with that. So when we talked about the group homework, that we were talking about how to break down a signal based on how many bits of resolution you get. So, and the one I'm going to show you here is a 4-bit, I think. So 4 bits, you got 0, 0, 0, 0, and then 0, 0, 0, 1, and then 0, 0, 1, 0. All the way up, counting binary, up to 1, 1, 1, 1. So 16 counts, 0 to 15. So the smallest that you're going to get is 1/15th. So, if you divide your signal by 1/15th, that's 6.67%. Is that okay? Probably not, but you never know what your application is. Whereas if you get up to 16-bit resolution, then you're dividing that each item that you're reading, like voltage or amps or whatever you're reading, you're dividing it by 65,000 and you're getting much better resolution. And the example is here of a 4-bit conversion. Once again, here's my bits, my binary counting all the way up from 0 to 1, 1, 1, 1, which is 8 plus 4 plus 2 plus 1, 15. So I divide it. And then, 5 volts gets cut into these increments here, and because it's 5 volts divided by the percentage that we showed here, 1/15, that's kind of the gross. With 4-bit resolution, kind of gross. So it's gonna round here. So if you got 3.2 volts and you're falling in the middle here, well, it can't read that. It's gotta land on one of these numbers here. If you really need to read 3.2 volts, you're gonna need a bit higher resolution. If you need to read 3.21 volts, you're gonna need even a higher resolution. So that's what you gotta think about. Okay. All right. So moving on, we're going to be talking about our analog I/O modules in our programming. Okay. So the two types, excuse me, of analog input modules are voltage sensing and current sensing. We're going to start this week using voltage sensing. It's all set up on the controller where it's going to read voltage. There's a little dial that we can dial up the voltage 0 to 10 volts, and that's what we're going to be reading. As we move on next week, we're going to then be current sensing, and we'll be using a transmitter, a temperature transmitter, and then we'll be using a thermocouple module. Okay. Excuse me. And so the thing that to recommend to realize, and we'll go over it again, is that the analog is going to be a linear or a proportional measurement, whereas I say thermocouple demonstration here. Oh, I need to launch my VLC media player. Let me just do that real quick. Hang on. I'll open my capture device. I'll do this and none of this. Sorry about that. Usually I'm all good to go on that. Ooh, didn't like that at all. Let's just go right back to this. Is that gonna do it? Oh, yeah, it is. No. All right, I gotta pause this for a minute and fix this. Hang on. All right, that was no time for you, but that was a couple of minutes for me to get that going. Anyways, talking about it's a thermocouple demonstration. So this is a thermocouple input module, which is very similar to the analog module that we're using, and we'll be using this next week, and it's got some thermocouples in it. But the wiring in here is going to be a little bit more complicated, or maybe a little bit different, I guess, than the wiring that we've done on sourcing and syncing input and output modules, digital input and output modules. And so the thing is to realize is that this is not a linear device. It's a thermocouple, and thermocouple response is not linear, whereas the analog that we're wired into is going to give us a linear or proportional curve, and we'll be doing some math on that here shortly. Okay, so I'm going to come back here again. That's kind of what I was talking about, my thermal demonstration. Let me see, this is still going. Yeah, we're still going. All right, here we go. That's still going. Wow, that messed me up a little bit. All right, analog input and output devices have an infinite number of states, and so we're typically talking on our modules of, you can send them 0 to 20 milliamps. I don't see that much. A lot of items you see are set to 4 to 20 milliamps it could read, or 0 to 10 volts. That's kind of what we're using. That's what you see a lot. And the analog input accepts analog signal and converts it to the digital signal. So you're going to have that conversion in there so the PLC can use it. And the analog output module does the opposite. It takes the digital signal, the PLC is like 101s and 1s and 0s, and converts it to an analog signal. So 5 quantities, for example, that you might want to measure that are analog, that would have potentially infinite states, or temperature, speed, pressure, level, weight, position, things like that, because temperature can be 20 degrees or 21 degrees or 22 degrees, or depending on the resolution, it could be 22.5 degrees or 22.5687 degrees. Just depends on what kind of resolution you want or what kind of resolution you need. The main element of the analog module is an analog digital converter, A to D converter. So a couple terms: bipolar, can accept signals that swing between negative and positive. We're not necessarily using that today. We're this week's, in the coming weeks, using 4 to 20 and 0 to 10. Unipolar is what we're doing. We accept in the positive. And then resolution refers to the smallest change in input signal. That's what we talked about whether you're doing unipolar or bipolar, you know, -10 to +10, but let's say we're using 0 to 10, and then we showed you the way to calculate your resolution. And for our needs, the resolution is going to be good enough just to kind of demonstrate it. Unlike voltage input signals, current signals are not as sensitive to noise and typically are not distance limited. So if you want a 4 to 20 milliamp sensor, the benefits are that if you get noise in this analog, if you get noise in digital, it's probably not a big deal because it's just on or off. It's just sensing current. But if you get noise on your analog signal, well, that noise is going to mess with that signal, and that signal, especially if you have a high resolution, is going to really screw up, what you're reading and the numbers that you're getting, right? So the current sensing power can be supplied by the sensor or by the analog output module. So usually when you have the module, there's sensor supplied power or module supplied power, there's usually a little dip switch on the module that you would click up or down, saying that you would want how you want to supply your power, okay? It says twisted pair is normally recommended for the analog, and we'll talk about error checking later. The main element of the output module is the opposite, the D to A converter, and analog outputs. Now think about that. But we do a lot of analog input. So the items that I mentioned right here are going to be quantities that you're going to measure: temperature, speed, pressure level, weight, whatever. These are inputs, and so it makes sense that we would be measuring so many things. Now, when you want an analog output, there isn't quite as many applications maybe of an analog output, but they're out there. If you want proportional control of a valve, instead of just the valve being on or off, or if you want proportional control of some type of a motor or something like that, you could use an analog output module. So it's out there, and there's certainly applications, but usually analog, you're thinking, I want to measure something, okay? So, if you talk about analog I/O control system, and in a few weeks we'll get into like more of a PID control, to where the system feeds back on itself to get to reach a set point. In this case, they're showing like a valve is opening to fill a tank or something like that. It says initially opened 100%. As the fluid level of the tank approaches the preset point, it would modify the output so that it would start slowing slower, so that you could be sure to hit the level exactly, versus if you just left it on and then all of a sudden it reached the sensor and you shut it, maybe it would just overfill a little bit. And like I said, a lot of times maybe it doesn't matter if it overfilled an inch or half an inch or 2 inches or whatever by the time it shut off and all this extra water ran out, versus if you really needed that level to be exactly to whatever resolution you want, then you could use the analog output to start dialing this down. And what we do is temperature control, where you're heating something up and you want to rapidly heat it, and then you want to start slow that heating down, because sometimes if something's being heated, it takes a while to on your heat capacity to absorb that heat, and then it would heat rapidly, and then it might heat slower depending on the temperature of it. And so that's where we're going to get into our PID temperature control of heating and cooling, and that's where analog is going to be good. So the analog number systems, we're going to get a new data type, our real numbers. That's our floating point. So we can essentially get not infinite, but almost infinite, or a very large number of different outputs and inputs. All right. Then we're gonna have a decimal point, basically. The analog I/O, when you set this up, there's channels per module. So our analog is set up with currently set up with 2 channels. We got a couple of gauges, a couple of dials. We're going to be wiring into this in a week. We just want to be sure we don't blow anything up. and there are voltage and current signal ranges that you want to set up. And like I said a minute ago, we're talking about 4 to 20 milliamps, and 0 to 10 volts are probably what we're going to be working with here for our current and our voltage ranges. Okay. There's some other things here that there is some input protection, and we talked about our resolution, and you can dive down into these analog modules in the thermocouple modules, and we will a little bit as we start getting a few problems. Now, I'll tell you a problem right now is that they're not fully calibrated, so we're going 0 to 10 volts, but the trainer is not producing all the way up to 10 volts. So we can put some offsets or some kind of calibration, I guess, in there a little bit, but really we need to get in there and calibrate our voltage supply to be sure that we get 0 to 10 volts, okay? But that's stuff that if you were setting up and measuring analog, and if it did matter that you needed 0 to 10 volts exactly, then you want to get in there and be sure that it's producing what you want, okay? Common mode rejection. Noise is generally caused by electromagnetic interference, and like I said, on a digital input and output, who cares? It's probably not that big a deal. It's going to be on or off. But if you pick up any noise and you have parallel wires, a twisted pair that are running out of sync, noise would be picked up equally in the pairs, and it would be rejected. So twisted pair wires are used to ensure that noise is equal on both sides of the wire, and the module will pick that up and reject it, and that's what we'll be setting up. So when we go and set up our cars, you can go through all these connections. I got a little item here at the start of the lab that just has you go and set up an input and output card. Be sure that your input's reading and that your gauge is that your analog gauge is moving, pushing the output. But the main thing to do right here is to understand the configuration. Now, we're using channels 0 and 1, so here's the first thing that messes them up. Be sure that you're hooked up to 0. If you're turning the dial on channel 0, be sure that your PLC program is addressed to channel 0, or your channel 1's got to be addressed to channel 1. Same for your outputs. 0 is not 1, and 1 is not 0. So that's the problems that we have, is that people set this up and then they don't address it correctly in their program. Now, the input range here, that's what I was talking about, 0 to 10 volts or 4 to 20 milliamps, and we could throw in some sensor offset here to if the manufacturer required that, or we had some situation, or we need to, in a sense, calibrate it, get things working and reading like they should. We could offset the sensor, and we'll be doing this with our thermocouples more than we are here. But the big thing is the scaling here, and that's what we want to be sure everybody understands, is that this does a lot of cool math for you. So if your sensor reads from 4 to 8 volts, you can equate 4 volts to, say 100 degrees, and 8 volts to 110 degrees. So let's say your sensor then reads 6 volts. Well, that's right in the middle of it. Well, this card will automatically do the math for you and tell you that it's 105, if that makes sense to you. 4 to 8, if I split the middle of that at 6, I split the middle of this, it's at 105. Well, you're like, oh, that's easy to do. Well, yeah, but if it's 4.1738 volt or 4.17 volts, well, what's that? Well, you could figure it out, and we're going to do it in a minute. But the card automatically scales what the voltage reading is, and it produces the output that you want. You want PSI, you want a degree Celsius or Fahrenheit or something like that. It pushes out like that. So the first part of the lab kind of goes through that and talks about it. Okay, so I got some scaling example here. Like I said, the analog traders might need a little bit of calibration. We can take a look at them and be sure. So we're going to talk about some scaling examples. We're going to need to do a little extrapolation. So you have these in the handouts that I gave you, and I'm going to go through them fast, but you can always rewatch this video to be sure that you understand what's going on. So what I have here is an analog temperature sensor. It's going to read from 0 to 212 degrees. So, 212 is like right in the middle here. That's where my 212 is. So I got Fahrenheit degrees on here, 0 going to 212. And the voltage is going to be scaled 0 volts to 10 volts, okay? VDC. So it's proportional, it's linear, because that's the way that these analog works. So that I get a nice, proportional line here, and we're not going to dig into all your algebra 2 to be sure that the correlation is correct or anything. We're just going to say it's going to be linear. Okay, let's just assume that. So it says, what is the temperature in degrees Celsius when the card is at 6.8 volts? So basically, that's saying is, here is, at 5, you can follow this up, or at 6 you can follow, but in 6.8 you can follow it up, and it looks to be, something less than 150 degrees. But we can figure out what that would be at 6.8 volts. And the way you can do that is, if you think about it like a thermometer, I can do vertical, is that at 0 degrees, it reads 0 volts. At 212 degrees, it reads 10 volts. So 6.8, it's more than halfway up. So it's going to be more than halfway up. It's going to be more than 106 degrees, 106. But what is it? Well, you can just create a ratio here because it's linear. 212 degrees is to 10 volts. That's my ratio. 212 is to 10. As x degrees is to 6.8 volts. Okay? You can cross multiply. So 212 times 6.8 equals 10 volts times x. And then you can just do 212 times 6.8 divided by 10, and x gives you 144.1 degrees. And if you did that and you looked, 6.8, yeah, it's below 150. It's probably, it's kind of the way that I've got this drawn, that seems pretty reasonable, 144 degrees. But to get into it a little bit better, to understand what's going on, is that this is a linear line, and so therefore it has the equation y equals mx plus b, where m is your slope and b is your y-intercept. X would be my axis here, dc. Y would be my axis here of temperature, okay? So my slope is y2 minus y1 over x2 minus x1. So my y's, which are here, and my x's, which are here. So y2 is the highest that I was going up is 212. The lowest I was doing is 0. So it's 212 minus 0. The x was 10, and then the lowest was 0, so 10 minus 0. And so you get 212 over 10 divided, so it's 21.2, okay? And that is, degrees per volt, by the way. But we're just realize that it's got the units of degrees on top and volts on the bottom. But it's 21.2, okay? And so that is your, you're up and over, 21.2. And this is just, once again, going back to your, I believe, algebra 1 and geometry 1, okay? My B is my y-intercept, okay? Which is going to be, in this case, when this gets here, it's just going to be 0. It's going to, because it starts at 0, 0. The y-intercept is 0. So I get the equation y equals 21x plus 0. You want to check it? Well, you can plug 6.8 into here. 21.2 times 6.8 is 144.16. So by having this equation, I can quickly do the math. What is it for? What is it for? Just plug 4 in. 21.2 times 4, it's 84.8. Bang. Instead of, you could do it here as well. You could set this to 4 volts, and then you could ratio this and get your number right here. But if you have the equation of the line, it's y equals mx plus b. You can do this. Now, that is what this is doing for you right away. and we're going to talk some more about exactly how it's doing this, but it's basically doing all that math real quickly to generate, the equation of this line, and then when it reads in the voltage, depending on what range you want, what range of voltage you give it, and what range you want to do, it's then kicking out the number for you of a pressure or temperature or speed or whatever you want. That's the math going on behind it. Okay, let's do another one now, because it's really not always that nice that you just saw. So this one says an analog pressure is going to read from 10, which is here, to 155, which I've got up here, okay, and from 1.5 to 8. So notice from 1.5 and 10, that's the first point, 1.5 to 10, all the way up to 8, because it said 8 volts, and up to 155, I threw in my nice, happy, linear, straight line, saying that's going to behave like a line y equals mx plus b. Now, the manufacturers don't use it less than 1.5 or more than 8, because who knows what the heck's going on the outside of that. It might no longer be linear, and the sensor might not work like you want it to work, okay? And so it says, what is the PSI per volt? So that's our slope. It is going to be, Y2, 155, minus 10 is 145 over X, which is going to be 8 minus 1.5, 6.5. So when I divide that, I get 22.3 PSI per volt. So every volt that it goes up another 22 PSI. 2 volts, 44.6, 3 volts, 66.9. So that's my relationship. More voltage, that much PSI each time. And that is the slope of this line right here. It doesn't count the area out here or the area out here, because that's outside where the manufacturer said that we want to use this sensor. We're not reading outside of there. So we have y equals mx plus b. Well, now we need to figure out what my y-intercept is. So if you remember, what we can do is we can solve this equation for either this point or this point, because we know these points here, and then solve them for b. Okay, so I'm just going to pick this point right up here. This is y. The y was 155. We already know the slope from up here, 22.3, and the x was 8. So I can solve this now, and I start working the math here. This is 178, subtract 178.4 on this side, and I get b is negative 23.4, which makes sense. That it looks like if this is coming down this way, it's hitting down here at a negative number on that slope down here. It's hitting down here at negative 23.4. So that does make sense that the y-intercept is negative, okay? So it says, what is the voltage at 97 PSI? Well, we've got the equation of our line right here. Y equals 22.3x minus 22.4, and it wants 97 PSI, which is our y. So we're just going to backwards solve this. Y equals mx plus b. 97 equals mx plus b, and our b is negative 23.4. So what do? We're going to, this is minus 23, so you do plus 23, and then you divide it by 22.3. So 120.4 divided by 22.3, we get 5.4 VDC. And that is, once again, going to be, 97, right here. And then you come down right here on the other side of 5.5. So yeah, it looks like it's about 5.4 VDC. It looks pretty good. If you have the equation of this line, there you go. Now the difference between these two is that this one started at 0 on the volts, and it started at 0 on the Fahrenheit. So it was just really easy to see, if you wanted to kind of lay it out either vertically or horizontally, and you could ratio it. Well, this one doesn't ratio like that. You can't run the ratio on this because it doesn't start at 0. Okay, hopefully that makes sense to everybody, that this cross and multiply doesn't work. Well, you can actually set this up and figure out the ratio, okay? But then you got to remember, whatever your answer was, you're going to need to add or subtract where it started, okay? And so it started here at 1.5, if that's the way that you solved, or it started here at 10, if that's the way that you solved. So doing the ratio thing gets more complicated because this is not going through 0, 0. It's shifted over and it's shifted up to that point, okay? So the y equals mx plus b is going to give you, the response that you want. So now when we go back to this right here, we have, I hear you, thank you. Oh, I'm sorry, it's right here. So when we go back to this, we've got an ugly one here. This doesn't start at 0 volts. It starts at 4. The low engineering is not 0. It's 100. So basically, this is doing 8 minus 4 divided by 110 minus 100. This is getting your slope. And then it needs to know, how this is getting laid out, y-intercept. It's creating your equation. So that, once again, when you read a certain voltage, boom, it runs that y equals mx plus b formula for you and gives you your result, your pressure, your temperature, your speed, whatever you want, okay? So if we take this a step further and it says, if the pressure reads 1.3 VDC, and basically what I did right here is I took my line and I just made it a little bit bigger. So this goes up to 100. So basically I just kind of chunked out this part here and threw it on here. I didn't give you the whole thing. So the squiggly mess down here that starts at 1.5, that's what I got right here, 1.5. The squiggly mess starts here at 1.5. So we're going to say, well, what if we're reading below what the manufacturer recommended? Because we're reading at 1.3 and the manufacturer said only read at 1.5. Well, so that gets ugly. I mean, if you want to go ahead and try to, look at the ratio here and try and work it out in your head, what the ratio is, and then you got to offset it by something that's 1.3 because we're not starting at 0, 0 here. I certainly could pound the math out for this. Or I could just, run through and generate the equation of the line, which we already did, at y equals 22.3 x minus 23.4. And I can just plug that in at 1.3. 22.3 times 1.3 minus 23.4 gives me 5.49 psi. Now remember, this said it wanted the range of 1.5 VDC, and then they were recommending that was going to read at 10 psi. So, but we're below that. So now we're going to be reading 5.49 psi. That's less than the psi the sensor is rated for, but it's still going to give us something there. It just might just be aware that we can use it. It might be a little. It might have some error in it. We don't know, because if that's the range of the sensors could still work outside of that range. But this is really getting, to be some more complicated math, that this right here, you set your high and your low, it does all the math for you. This is your x-axis, this is your y-axis, the range of your x-axis, the range of your y-axis. Boom, it does all the math for you, okay? So that's what that is showing there, okay? So we'll be making an add-on instruction in this lab, and it's similar to, I think about a function block that we did for the Siemens, okay? When you make this add-on instruction, okay, the add-on instruction will pop up here on your user. Let's see, my add-ons. I got one right there. Scale with parameters. I've got this instruction that I made, and it's just like any of these other ones here now. I can use it whenever I want, okay? So if I came down here and I wanted to, let's see if I can get that to come on down. There, I added it. Boom, it's there. I've got this to use now if I want to use it, okay? And then over here, I can check into it. Like I said, it's like a function block. If I go into here, it's got code within it. And so now I can use this as many times as I want. You know, do I want to do another one right here? Let's just click that. Boom. I can use it again and again and again. It's like I said, like the way that we learned it before is a function block, okay? And so that is one that we're going to be making. So a scale with parameters just basically does the math that we just showed here. It subtracts, you know, the x high, x low, y high, y low. It gets your slope. It figures out your y-intercept, you know, and so and then that way, whatever you put in here, it basically does what this card is doing right here, and that's what it's talking about here. You know, it's going to take your value of voltage and whatever your input min and input max and scaled min, scale max, it's going to scale it all out for you, and it's going to give you an output. So we're going to create a little something to do a scale with parameters, and then we'll be using this instruction in further labs, okay? So it basically says, like I said, it's doing the analog cards, that was the high-low variable for the signal, and then the engineering just ratios everything, figures out your slope and everything like that. So hopefully you understand that math that we just went over, so that when you start trying to figure out what's going on with these thermocouple cards, with these analog cards, with these temperature transmitters and everything like that, you know, this is kind of some of the math that is going on. Okay, so with that said, it says quiz and lab, and take a look at it. Take a look at the reading on the D2L, and that's what I have for you.